Good afternoon. It's Monday, 2023 in March. Overcast, rainy, cool, fresh, not unpleasant. And so today, this is reading some more from the Path Integrals and Quantum Processes. And it's good to have a book that's quite thorough and covers such a complex subject as the path integral with regards to that. It helps to incorporate a lot of the concerns, the conventions, the forms, the compromises as they are, which are always to be avoided as they reflect that something had to give for that which becomes fixed and that which becomes well defined or well behaved. That then is been good to in the reading of the developments and the derivations to consider the author's style with respect to that which otherwise goes unsaid, the implicits in the context, the things that go without saying, the things that are expected to be known, or the things that are unknown. Those things that reflect the inner and outer products of these projections of facts that you could call a knowledge representation or a space of knowledge that affect in effect the learning mountains that is our purview that we can find above and beyond these learning hills that we've so gained the rise that. As we arrive at these learning hills in the development of our stories of knowledge and how we got there and our conscious approach to this conscientious sort of analysis and the reasoning about these things, that then what goes on in terms of the talking out the context, both the linear context that we are in and which carries us to common understandings and those things that we can agree that we've agreed upon, and then also that it helps to reflect the richer and wider course of what would be trails or ways that various sorts, investigations, and analysis could also lead us in terms of how then it's arrived at what are these working terms for a working theory. So there's pure theory, and pure theory is this, in a sense that everybody has a pure theory, whether they know it or not. And then there's the pure theory, so singularly qualified as that it reflects that if there's a truth and a real truth, then it's fundamentally a pure theory. And then there's our applications, the applied theory, and that's again, insofar as the personal and the subjective goes, that it is our objectifications and our both how we internalize such forays and essays, and also how we externalize such means to the applied. So that then in the milieu of our pure theories and our applied theories and our working theories, then it gets into that when we talk about the science and the scientific method and the philosophy of science, then there's the experimental and the fundamental, as has been discussed here. And then there's what gets into the empirical and the formalized vis-a-vis what's defined and derived in the mathematics, where our mathematical model is ubiquitously successful and it advises all that it equips our physical models with in terms of tractability, of fungibility, of sensibility, qualitatively and quantitatively. That then what is otherwise the quantitative, when it's reduced to the qualia or qualitative, has that there's to be arrived at then beyond the empirical, that we arrive at how our empirical becomes as of what was fundamental. And so it's a usual regular course to try to figure out what is the least working theory that's involved, because nothing's without a cost. Nothing is without its occupation of resources, and we only have limited resources, and thus that in these manners, it gets to where it's possible to figure out what is to be a working toolkit that will suffice for most purposes, and then to make it so that then in the higher course of development, towards the improvements of the mind that result the ability to encompass a theory of all things into one thing, for the theory and the logic of the mathematics, the physics of statistics, that we can arrive at what gets into these distilled writings and what makes for a linear curriculum and the digestible, which can be internalized and as well externalized. That as well, it's been enjoyable to read these sections after the author Swanson's definitions of the objects of the models and what so follows linearly, and then as what goes into the concerns into why there's that not all the operators are closed, not all of the systems are closed. There are open systems and there are incomplete operators. There's this degenerate, which is these primitives that we have built together as fundamentally entangled and fundamentally of singular entities that have their sides that are only their half shadows, or otherwise in metaphor. That then this idea of the deconstructive analysis is really the act of inferring and deducing why there is from the empirical this fundamental, and then thus how from this fundamental there's arrived at this empirical, and then what it means in terms of the interactions of here the forces of a unified field theory of a physics, how that arrives, that it's possible that our mathematical models yet remain so tractable that it becomes possible to make it, in so far as that they're fungible, that they're on a higher order tractable, and result that then we can really apply the lever, the simplest machine, the lever, after the inclined plane, I suppose. The inclined plane is a simple machine, given various notions of what are the most simple in machines, fundamentally. How it's so arrived at that our machine of work, of mental work, can arrive at what makes it so possible that we get above the stuff, and it's possible to both know what we're talking about and how we're talking about it. And otherwise answer all these question words for pure theory, the applied theory, a fundamental theory, an empirical theory. So we got to this earmark here, and I'll pick up where Swanson left off after we've been discussing the Jordan measure and how it's these iota values, and that there is a non-standard formulation of continuous domains for modern real analysis that has such a one-dimensional Jordan measure that also has a sigma algebras, and this is not what you'll find in the usual curriculum, because the usual curriculum is very particularly standard, and there's lots involved when you want to explain the continuum in its replete definitions in a formal way. That the author so continues. Some aspects of summing over paths can be made clearer with a modicum of effort. One of the chief difficulties in constructing a rigorous measure for the continuum version of the path integral is the presence of the I in its definition. The oscillatory nature of the exponential creates difficulties in including unruly paths, i.e., non-differentiable and discontinuous paths, since the exponentiated action tends toward a distribution. Here we've talked before about the tendencies and the propensities of things with regards to the oscillating and in the restitutive, and the attenuating and the dissipative, and how this accumulating in terms of the tendencies has of the origins of things, whether the origin is a font and out from it comes things, or the origin is a sink and into it goes things. And then we also talked about things like about the particular properties of between 0 and 1, the unit interval, and multiplication of quantities within that interval, they get smaller, whereas the addition of quantities have is about between 1 and -1, that 0 is in the middle, that there's this propensity and tendency towards 0 in the products, while there's propensity or tendency towards 0 in the differences, the inverse of the products. Again, just reflecting on why the operations of arithmetic may degenerate, have that they're tussled, they're unknotted, they're gently pulled apart without destroying their form, what so results how they're woven together and make an integral form. Here I often use the word integral to mean as of a whole, and a seamless whole in terms of the integral, which is a different thing. Just to note that the integral here is of the operations of arithmetic, but they're not necessarily fundamentally so. There are models of them, the inside and the outside, that have these various ways to look at them, like so. And so then we have to deal in this realm of quantum numbers with the central limit theorem. And there's also an entirely non-standard yet perfectly modeled and extremist thing of the uniformization limit theorem. That for what comes after Bayes, then there's Jeffreys, and there's also what later gets into how that's parastatistics, the degenerate of the statistics that still must add up because that's how it is. And that the all the area under a distribution that defines a probability distribution equals 1. And then we model the event sometimes as that is the impulse. That here, beyond how we have to talk about sometimes that there are non-standard models of probability theory where there are some non-standard functions that define or describe how it's possible for a given set or group or collection or their iteration of elements has more than one function that defines its PDF or CDF or MGF. This is again in the realm of why when we have to deal, for example, in these finite quantities only, then the linear, but that the nonlinear, and these sum of harmonics and functions, that it gets very complex again, but it's usually only these opposite concerns that both attain to each other, yet never are complete in terms of each other, yet insofar as they are complete ultimately in terms of each other, why we have to address what's called the inductive impasse. The impasse is like a crevasse. And the idea is that if you fall in the crevasse while traversing a glacier, it is sudden and instant doom. There's no way out. Whereas the idea is you get over the crevasse, that here the crevasse represents an impasse. That is an impassable thing. And so for these terms, then there's basically the idea that induction carries out for things about the integers, and we use them to apply things about the laws of large numbers, induction. But there's still that deduction, analytical deduction in the close and in the far, helps build up these, correspondingly, these near field and far field descriptions, which result how that we can consider abstractly that the arc of the sky goes over that. Again, that's metaphor, and metaphor is useless, or eventually, ultimately, metaphor is useless. We don't have the strong metonymy, but here in the metonymy is the idea that for the laws of large numbers, there's these weak and strong laws of large numbers. And so when we talk about the central limit theorem from probability theory and the usual development of the Gaussian distribution and how that all adds up together, and how that's built up as out of integrals of the exponents according to probability theory, the usual integrals of the exponents that define the most well-known shapes and scales of distributions, where there's about 20 or 30 usual distributions by their shape and scale that manifest and evidence themselves in all such things called model fitting. When you fit data to a model, is by these estimates, what we call the estimators and maximum likelihood estimators. of likelihood estimators. That beyond the normal distribution, there's all kinds of things to do with continuous and discrete probability distributions, and I don't really recall, but there's beta, there's Poisson, there's Gauss and the normal, there's products of the Gaussian normal, there's chi squared, and about t in students and Fisher's tests about the standardized and normalized in the normal distributions. There's Weibull, and there's the logistic, their power distributions. It made me very happy some years ago when I was able to find on the wiki or otherwise that what I otherwise only found in one of my textbooks on probability theory was a list of the 20 or 30 distributions that by their shape and scale parameters establish what are the usual, most often found because of counting arguments in random processes and the stochastic, these things that arrive at tractable means for statistics to establish a statistical experiment that according to something like the central limit theorem, it's possible to then derive from a statistical hypothesis, kind of like our physical hypothesis that might be falsified, whether it's possible to invalidate the original hypothesis that something has a given likelihood of falling close to its mean. So here then, and especially when we get into the non-standard, and there really concretely are these ways to define that a given probability distribution has after, or before rather, the degenerate of these points from a line, or that there's a distribution that has a both continuous version and a discrete version. That these are the kinds of things that get into how there are these higher fundamentals that result for what otherwise is an entirely solid platform, and what for some is the foundation. There's a deeper foundations and down into true foundations. So with that as being kind of a path and a trail, in a roundabout way, we return to Swanson, and he says the oscillatory nature of the exponential creates difficulties including unruly paths. About the rulio and the regular, non-differentiable and discontinuous paths, since the exponentiated action tends toward a distribution. Notice that he indicates both it tends toward and that it does where that suffices, and then that only does where that doesn't suffice. A simple exclusion of the unruly paths would be incorrect. This is so because while the differentiable and continuous paths are everywhere dense in the set of all paths, it can be shown that taken alone, they are inadequate to give a correct evaluation of the path integral. In point of fact, a careful analysis of this situation shows that these paths form a set of measure zero. This is a set of measure zero, is that in the measure theory, there's the measure theoretic and the discrete in a continuous domains set with measure, that measure 1.0 is axiomatized after least upper bound axiom, after the ordered field and Cauchy and such. The results that measure 1.0 has that the line segment of length 1 has measure 1. There's that any countable set has measure 0. Or and that's something to say that otherwise there are non-measurable sets, and these usually have either measure 0 or not a finite measure. That's the whole point of how measure theory is applied for physics, and because it's the mathematical models that so equips all such notions in the other theory, physics, that here the author relates how in the standard way that measure theory is built up and out after standard real analysis, after the measurable and non-measurable and measurable and non-measurable sets, that then in these cases the measure is 0. The situation is much like that of the real number line, where the set of all rational numbers can be shown to be a set of measure 0, even though they are everywhere dense in the real line. This of course is a very relevant thing, and I discuss it quite a bit in the talk about standard real analysis and non-standard analysis, continuum infinitesimal analysis. Unfortunately, because the exponentiated action tends toward a distribution, or because it tends toward a distribution, that it must be read each of the ways. The path integral defined by 2.55, that's after the Gaussian analysis, the limit of I alpha t equals pi I alpha delta alpha as t goes to infinity. 2.55 prevents the definition of a well-behaved measure. Now, as we talked about, the Jordan measure, you can figure out a way it's well-behaved. As we talked a bit about the Dirichlet function, you can figure out a way about how it's well-behaved. Involves extra foundations, the beyond the fundamental, ultra fundamental, it's possible, but here it's not available. And therefore, an alternate scheme must be found if a mathematical definition is to be made. If a mathematical definition is to be made, that we define things so they're finite. It is the oscillatory nature of the path integral that gives rise to the distributions. It's the behavior of the wave that gives rise to the oscillatory nature of the path integral. If the oscillations were suppressed, then it might be possible to define a sensible measure for paths. It is with this hope that much of the rigorous work done on path integrals defines them for Euclidean time. This means that the integrand of the action undergoes the so-called Wick rotation, which amounts to replacing t with minus IR, or minus I tau. That must be minus IR. So here he's talking about equipping the usual mathematical model where everything's universally parameterized by one forward time, and the only possible thing that can happen in terms of time dilation is that something slows and it later joins time, forward ray of time. He's describing equipping this model with a model as about the symmetrical and the reflective and the reversible and irreversible as about how this Wick rotation is framed up in the Gaussian complex analysis, about what this, as he put it, unruly paths, is that that it's the oscillatory nature of the exponential, that he's so defining a transformation in coordinates, what results then is possible to help add up in these cumulative commutators, how they add up and about and around, that this modeling of time as this other quantity, negative IR, is only insofar as that such contributions result that it's a way to implement a simplification of the terms, because such results of the restitutive and the oscillatory enable it to be brought back together and considered negligible. In effect, and I hope you please excuse me that I'll always try to read the author's writings non-judgmentally and directly and as fully and clearly as I can. And I'll try to read them in a voice as if expositing upon them, and I hope it's clear what's from the book versus what's out of my mouth, which I also will exposit upon and make clear. It is with this hope that much of the rigorous work done on path integrals defines them for Euclidean time. This means that the integrand of the action undergoes the so-called Wick rotation, which amounts to replacing t with negative IR. In effect, the path integral is analytically continued to imaginary time, evaluated, and analytically continued back by the inverse Wick rotation, R goes to IT, to yield the final result. So here he's describing that it's still that is a extension of the model, where otherwise the time, this quantity, has a very, very strong real attachment to things forward, the ray of time. And that's, at least in part, for people who have a clock hypothesis, and build a space-time of 3 dimensions plus 1 time dimension from a hologram of 1 dimension that's in space, with the fact that there are the infinities and infinitesimals which build a rotation as around it, so that that 1 dimension suffices to encode an actual Euclidean space in 1 dimension quite thoroughly and interestingly, as about the long line. And then that time is just that space goes on forever, time goes back forever, and that evolution of them together results that it's possible to build from a hologram the entire 3 plus 1 space plus time, the about 3 and 1/2 space plus ray of time, into one structure called the hologram, which is for a mathematical universe hypothesis. Why? Because of a principle of least resources. That's the simplest number line that encodes everything. Again, now that's quite different here and quite less mathematically justified by what we've been talking about so far. It justifies itself by itself. But I just would have liked to introduce it so that you know where I'm coming from. So he describes the application of this method in our model with its physical interpretation, and helps describe why it has a mathematical interpretation, the results of physical interpretation, and also how the mathematical interpretation's vestiges are left out so that it doesn't become encumbering the interpretation otherwise of the quantities otherwise in the rest of the model and all their models together. The necessity of this analytic continuation arises from the need to evaluate the generalization of the oscillatory Gaussian integrals first encountered in section 1.5. There, the integration was defined by an analytic continuation identical to the Wick rotation. Under the Wick rotation, the form 2.50 for the path integral becomes z equals integral from q sub a to q sub b of the quantity script d, capital D, bar sub q times e to the negative s, as was before, sub e over Planck h bar. Where for the simple case, 2.48, the Euclidean action s sub e, these are the summation of the action terms, right, is given by s sub e equals the integral from ta to tb, d in dr, of the quantity 1/2 m dq over dr squared plus vq. And here I'm reading r as it looks like scripty r, so if it's tau, I'll apologize. So I suppose that might be tau, where I've been reading that as r. I tau and I t. So tau is just as complement to t. Whereas also I've been reading an r with respect to also in the exponential with this wrapping around the analytic line of this principal branch of what comes out and down from complex functional analysis, that 2 pi is dimensionless. So then it's built up in this term of vanishing terms of dq d tau squared, the quadrature, as it were, and 1/2 times m times that plus vq, the volume q. So that being integrated over the course of the actions integrated over the time, the factors in the measure of the path integral become real under the Wick rotation. So that script capital D bar sub q equals limit as n, the parameter of how many infinitesimal line elements are in the infinitesimal line elements that are the line measure elements of this Jordan measure, which is these iota values, which is so founded. As limit as n goes to infinity, that goes to infinity, of m over 2 pi Planck h bar epsilon t, as we recall from the previous description, that quantity all to the n over 2. So it's basically building out this frame, and kind of like we were talking about the inductive impasse before, that here it's to this power of the n over 2, and so as that goes to infinity, then it's still bracketed down under these quantities. that the quantities under their conventions, under their notations, under their implicits, under their derivations, have it so that then this quantity times each of the dq1 dot 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 dqn minus 1 is read off as a support that in the infinitesimal analysis that it's added up back to a unity. But here though, that when we see something like n over 2, infinity over 2, by itself it's unsensical. It's underdefined as to what, in the way that it is sensible and sensical, is that it demands definition. And so here it's quite an interesting and what out of context would be an unusual term and underdefined, demanding all this context and these implicits and these various things that go into it to otherwise keep it from being unsensical. And then he flourishes after that, where epsilon sub tau is effectively d tau. Effectively. Now the effective is basically when the sense of a limiting a value of an expression that is close enough, that it's effectively infinite. It's effectively zero. It's effectively unity. These are the things that result in it being effective when in the sense that there are underdefined terms that would make it not so if they were able to affect that at all. But here it's indicated a sort of linearization of sorts. And you might recall some of my previous discussions about the limitations of numerical methods and approximation when it comes to closed forms and analytic solutions, that they are incomplete at best and wrong at worst. That there is this relation that the raw differential, the infinitesimal, that the infinitesimal in the sense of this whole of this infinite is essentially a unit in terms of its dispersion as of these integers. That then the dissipation as that one infinitesimal goes off and you count them up like integers goes to infinity. That's the same thing as that they in the course of passage of clock arithmetic, a non-standard Aristotle's continuum, or kind of like one that Peano has about put together, or iota values, or this, so add up this way as they do. And of course everybody's familiar with that when they took calculus in high school, and before calculus they took pre-calculus in high school, and they learned the definitional limit. And they learned that then as soon as we figure out that we can take these Zeno's arguments of the infinitesimally small that all add together to one, though most of Zeno's arguments are framed about methods of exhaustion, about halves and halves and halves again. That they admit solutions in related rates problems in terms of constant uniform time that's infinitely divisible by such means as methods of exhaustion or in classical constructions, that we learned that these infinitesimals between 0 and 1 are non-standard, and we learned that our complete ordered field is standard, and we learned that the definition of a limit suffices to thus make this infinitely divisible infinitude tractable, after it's fungible, after it's sensible. The Euclidean action is identical in form to the integral of the Hamiltonian, written in terms of q dot instead of p, momentum operator dot instead of p, the position operator, or as I read them. It will be shown in chapter 4 that this is no coincidence. Well, it reminds me of something I'd really rather know something more about, and that's spectrum analysis. So we got the frequency domain and the time domain and this kind of thing, and the idea of how they resonate harmonically is a key thing. And it'd be nice to define it in terms of that, so that we have a model of how this taut string is as well when its vibrations cease as a result of those, as well as it is just the winding on the string, as of a guitar string or something like that. it's also similarly when we even talk about the superstring theory, that these superstrings are arbitrarily small infinitesimals. They're just as arbitrarily smaller than the atom is to us. So it makes for a background of a continuous, effectively infinitely smooth, effectively. That's what superstring theory boils down to, is the open and closed superstrings are like the one-sided or two-sided points on a line, in a sense. And that's how they are supposed to work up, that they define for the discrete and continuous of our quantum particles in the range of the Democritan chemistry's atom and the electron theory. Why superstring theory is supposedly a real thing, because you have a mathematical model of it already. It's just infinitesimals to what if the atom were an infinitesimal, making for a smooth domain, and that makes for the effectively ungranular in that. These are the kinds of things that go into why it helps to explain then when we talk about multiple dimensions in superstring theory, that it just means these projective dimensions, like, well, this is where the Wick rotation lives, and then we bring it back. Because it still boils down to there's the 3 plus 1/2, or 3 plus 1, and simply as were, and for that all time processes are irreversible. It just so happens that there are many physical systems that are restitutive after they're oscillatory, or vice versa. That these are the kinds of things that go into helping explain why there's such the complexity of these mathematical models, and especially when the standard is in a way hobbled, in a sense that it always only, say, leans left when it goes around the triangle inequality curve or something like that. It makes things tractable after they're fungible, at the cost of that it's not complete. So it is no coincidence. However, for now, it is necessary only to notice that unless the potential is unbounded from below, large deviations from the classical trajectory as well as unruly paths are exponentially suppressed. They're attenuated. There's built in terms of their presence in the sum as physics of the term in a model of that this suppression is a form of, or censorship it's sometimes called, is a way to bring down this volume that is noise with regards to the signal that is so relevant, and results fundamental tones for what otherwise is the overtone. It's mentioned the word large deviations from the classical trajectory, and these are, we might consider in statistics it would be the outlier or something like that, but there's something to be said with regards to the central limit theorem again, and about the uniformization limit theorem, that, well, in the uniform and the attenuating, everything's flat, whereas in the uniform and the restitutive, everything has a mean. That there are two different things that reflect beginnings and ends, or the singularity, the origin, and the singularity, the asymptote, for invariant theory, and for symmetries in invariant theory, and this kind of thing. That is fundamentally, again, in the world of the complementary, what makes a complement of things. It's inverse and it's reciprocal, it's reflection. The Wick rotation makes a mathematically meaningful measure possible. It has a mathematically meaningful measure that doesn't have to admit what is impossible. It is worth noting that under a Wick rotation, the differential form of the Schrödinger equation for V equals 0, in referring back to the notions of the additive identities, when we mean 0 is the additive identity, so something's equal to 0 and we can deal with it, because its inverses have to go about 0. And then for a multiplicative identity, and either one of these is an identity, whether equals 1 or is equals 0 is an identity, and any form of any equations that result in anything else, you can call it an identity. But here for this additive identity about 0 and multiplicative identity about 1, then there's also the multiplicative annihilator about 0, with regards to sometimes we frame and stake these things to make it so they fall down from 1 and their products towards 0. And otherwise, we frame, intent, and state these things so that on either side of 1, that they add towards 0. Becomes Planck h bar squared, and again, like we were just talking about superstring theory, that the Planck's constant is just some orders of magnitude smaller than the electron. Over 2m delta, or nabla squared psi, I often misread that, triangle squared psi equals h bar of d of d tau psi. So psi is a Schrodinger equation, and you can express it in terms of when v equals 0, as the volume goes to 0, or as Heisenberg becomes ultimately precise, because when a photon hits the detector, you know its position momentum. It has a position momentum, you just can't know it because of the sampling, measurement, and observer effects about the fundamentally the ultraviolet catastrophe in electron physics and that. The quantizing of the quantum, the denormalization, which results in normalization here. He writes the psi in terms of another expression in psi. And the one is on the order of the nil square, or whether Planck h bar squared has analytical character, or it's 0. Whether it's measurable and adds up to something, or it's 0. That here it's in terms of the other one, that it's about the d tau, and then here that tau was, as he put it, same as epsilon q for the momentum operator, and that epsilon tau is essentially d tau. So this he describes becomes this in proportional to Planck h bar squared, has with regards to proportional Planck, and then proportional to 1 over 2m delta squared, or triangle squared, with nabla squared, with regards to d of d tau, that, and then that psi is parameterized in terms of tau, or here Wick's rotations t's tau, or tau's t, which is the diffusion equation that governs Brownian motion. So here's, we've been talking about the attenuation and dissipation. Then one notion is that the dissipation in a volume or area or a hypervolume is diffusion, that it's radiation, that it's as what conducts, that is conducted in terms of a perfect conductor all around, or one with a given material medium that has static and dynamic rates of these things. And that Brownian motion is essentially the notion of random motion. That for our variational principles, for the virial theorems, for the perturbation theorems, that these reflect that there's not so necessarily the static of a thing, so that otherwise it would just be 0. That then there's kind of there's restless regions about all these things. That so on, so goes on. Wiener was the first to construct a path integral representation for a Brownian motion and to show that a well-behaved measure could be defined. It has been argued using sophisticated techniques that the path integral has a well-defined measure in the Euclidean region, and this argument will be taken over in the remainder of this book. The interested reader is recommended to the books by Rivers and by Glim and Jaffe. At best, these remarks may convey the difficulty in making the continuum path integral of 2.55 a well-defined mathematical object. In practice, it is common to approximate the sum over path by using the subset of a piecewise continuous paths that are differentiable and continuous and that yield a finite action. In particular, the classical trajectory is believed to represent a maximum weight path. It is hoped, but unsubstantiated in most cases, that this approximation gives the most important properties of the quantum transition amplitude. In Chapter 3, the role of the classical trajectory in the quantum transition amplitude will be discussed for several extremely simple cases. This section will close with a derivation of the path integral representation for the transition amplitude in a simple one-dimensional quantum system with properties significantly different than those originally assumed. The system is that of a point mass constrained to move on a circle of radius r. Classical action for the system in terms of the angular variable theta is given by L theta dot theta. The Lagrangian, I imagine, the equals 1/2 m r squared theta dot squared minus v theta. V is the potential. The potential V is assumed to be periodic, so that V theta plus 2 pi n equals V theta, where n is an arbitrary integer. This would indicate a reciprocating system. The Hamiltonian has a standard form h of p theta comma theta equals 1 over 2m p theta squared plus v theta. The position eigenstates, where the eigenvalue problem finds eigenvalues that preserve the lengths of conformal mappings of vectors according to a determinantal analysis after a matrix representation of a tensorial analysis of product transformations of a coordinatized system and a vector space representation. The position eigenstates of the system are ket theta, and these are complete in the sense that the integral from 0 to 2 pi of d theta of ket theta bra theta equals 1. So here he's established an identity that the integral from 0 to 2 pi and the integral from 0 to 2n pi for any integer n of d in d theta of theta ket theta bra theta, where bra and ket are reversed, and this represents that there's this restitutive or the abelian or the commutative, that these are commutators and commutators rather, in this sense that he's established an identity 2.66 that the integral from 0 to 2 pi of d in d theta of ket theta bra theta equals 1. The configuration space representation of the momentum operator is bra theta given p given theta t ket equals negative I Planck h bar over r, the radius, times d of d theta, partial d in theta, which is the angular variable, with regards to the frequency and in the energy here, with regards to that a particle has a wave and a wave has a frequency. That quantity times delta of theta minus theta prime. So bra theta given p given theta t ket equals negative I, and this is this would be in and after the Wick rotation or what, but constrained to one dimension about the Schrodinger psi of this path integral representation of Planck h bar, the arbitrarily small but finite constant Planck h bar, and so that it's so normalized or divided by 2 pi, or insofar as it reflects as well its inflection, as it were, over the radius, inverse proportional to the radius of d of d theta times delta of theta minus theta prime. Because the system is on a circle, the eigenfunctions of all observables must be periodic. It is straightforward to show that the eigenstates of the observable p theta are no longer continuous but are indexed by an integer n, and are therefore denoted ket p sub n. It follows from 2.67 that the normalized momentum eigenfunctions for the system are given by bra theta given p sub n ket equals 1 over root 2 pi quantity e to the I n theta. These eigenfunctions are orthonormal. Bra p sub n given p sub n ket equals integral from 0 to 2 pi of d theta over 2 pi e to the quantity I times quantity m minus n quantity theta equals delta mn, which would be down to Kronecker, I imagine. And complete in the sense that the sum sigma from n equals negative infinity to infinity of bra theta given p sub n ket of bra p sub n given theta prime ket equals 1 over 2 pi, the sum of n equals negative infinity to infinity. So that's that one would read that they share telescoping terms in the infinite series of quantity e to the I n times quantity theta minus theta prime, all in the exponent, equals delta of theta minus theta t, where the Dirac delta is clearly periodic. The Dirac delta in its formalization here is built as after this notation of the family of functions that he has modeling it are these some exponential functions. So the Dirac delta is described as the limit of these functions, but there's any possible way to build the Dirac delta as you might want, so that there are ones that would have this particular action associated with them, and not to misuse the term action or something like that. That then with regards to what that otherwise trivially the Dirac delta is not periodic, it's an impulse, it's a spike at zero that's infinity. But here he's saying is that the system of equations that we have modeling that so work out in their extremis that they make a Dirac delta function, the non-standard function, have this property. These results can be used to derive the path integral form for the transition element, and these are our elements of bra theta b comma tb given theta a comma ta ket. That the transition element is in terms of this angle and time, and it represents some of these harmonics in terms of what's a wave, in terms of what's a particle wave duality. Well, I'll stop there, I suppose, reading from this for today, but got up to example 2.8 and so far, and then there's a bit to remain, and then that the next chapter has again some more of this the descriptive elements that go along with the formal elements is what result in the descriptive formalism, and also some of this was reread, from the early reading into what we're going into these developments and definitions, the end of chapter 2 there, and then as we went back a little bit and read and reread some of those other forms of the developments, it was possible to gain that these accumulating notions of a linear curriculum also build from us over time. It's kind of difficult to provide a linear curriculum that's unambiguous, that results always at the same receivable wisdom. But then there's also something to be said for that reading back and forth should always also arrive at the same kind of thing. And so it's really not so dissimilar in this development, the application of the tractability, after the fungibility, after the sensibility of these things that result that their applicability so follows from formally that not only that we can say, okay, according to mathematics, all the mathematical is right, and its interpretations of it outputs what's causal and what's acausal and what's correlative and what's non-correlative and da-da-da. That is so results that then we can define this in terms of a scientific experiment, that which makes it falsifiable. It's like, well, yeah, we built this boat and it didn't bust, so we did not falsify that this, according to this theory, it would not bust. Or did it with a bridge, or did it with other things. And so it's hopeful that will so follow that then it also helps reveal that the peeling of the layers of this thing have that sometimes the inside is better before you know what's underneath, because then that'll have built notions into associating causality with correlation according to coincidence. And there is such a thing, causality and correlation according to coincidence. And we can refer to it in that theory of one theory with the theory and the time and this kind of stuff of a hologram of space-time, and why that works out, that when we get into the higher level of Kaluza-Klein for 5 dimensions, so at least you have a dimension of projection to do all the usual analysis of first order approximations in the dynamics of relativity or quantum mechanics. But then as we get into what demands there are these higher dimensions for superstring theory, which is like, this has gotten too grainy, our smooth continuum, our quantum, we make another floor, 50 orders of magnitude down, we'll call them superstrings, superstring theory. That then it gets back into why then for the geometer's view that can be pulled back again is like, well, we only really need 3 dimensions if we have the right applications of what result, these fundamental tools, that then it can be possible, and at least in some contrived configurations of experiment and energy of experiment, that you can end up with a symbolic tool set that is able to work up a lot of these problems in much simpler terms, without necessarily loss of either expressive power or corrective power. That the blinders are on the horse, as it were, but it still doesn't trip, or this kind of thing. Let's see, if we might look to Feynman, Sands, and Layton. Let's see here, what do they say about a pair of dipole antennas? Now we come to an interesting case which shows up a possibly useful feature. Let us remark that one of the reasons that phase relations of oscillators are interesting is for beaming radio transmitters. For instance, if we build an antenna system and we want to send a radio signal, say, to Hawaii, we set the antennas up as in figure 29-5-A. We broadcast with our 2 antennas in phase. Where figure 29.5 shows the intensities in various directions from 2 dipole oscillators 1/2 wavelength apart. This is about the constructive and destructive interference in the radio wave, which is once dissipative and directional, but it's dissipative and omnidirectional. And then insofar as a waveguide or the building of a flagellum of sorts, or that this flagellation results in terms of the wave being driven by the power output of the dissipation of the driver by the horn of this thing, that then there's one in this diagram for phase alpha equals 0 and 1/2 period out of phase that alpha equals pi, where we get the usual notion that you work up periodicity in 2a or 2 pi, and that's how it is. So we come to an interesting case, and we set the antennas up as in figure 29-5A, and we broadcast with our 2 antennas in phase because Hawaii is to the west of us. Then we decide that tomorrow we're going to broadcast toward Alberta, Canada. Since that is north, not west, all we have to do is to reverse the phase of one of our antennas, we can broadcast to the north. So we can build antenna systems with various arrangements. Ours is one of the simplest possible ones. We can make them much more complicated, and by changing the phases in the various antennas, we can send the beams in various directions, send most of the power in the direction which we wish to transmit without ever moving the antenna. Just, it doesn't move the antenna, but at the same time, it's like, it had to be so manufactured. There's a big difference between being able to throw the pole, as it were, of the electrical conduit, as of the switch and flipping the switch. That it had to be designed that way. So the work goes into its design of the configuration of the experiment and the energy of the experiment, and then you got to fill it with what's called how many hamster wheels does a hydro dam turn, and then how many clock cats come down the feed according to hamster wheels turned by dynamos of the hydroelectric dam. Ours is one of the simplest possible ones. We can make them much more complicated. By changing the phases in the various antennas, we can send the beams in various directions and send most of the power in the direction in which we wish to transmit without ever moving the antenna, courtesy that the electrical fields and the magnetic fields of the Earth are already all set up in a quite larger cosmological clockworks observatory called the Cosmological Clockworks. In both of the preceding cases, however, while we are broadcasting towards Alberta, we are wasting a lot of power on Easter Island, and it would be interesting to ask whether it is possible to send it in only one direction First, we might think that with a pair of antennas of this nature, the result is always going to be symmetrical, so let us consider a case which comes out unsymmetrical to show the possible variety. And then they talk about 1/4 wavelength, and it gets into all this constructive and destructive interference. Talks about the lobes of the, if you've ever seen antenna transmission diagrams, they're kind of drawn out as shapes in terms of that the more you fill up power, they fill up as like balloons, these lobes, and then they radiate. Well, anyways, and then it begins section 29.5, the mathematics of interference. And so when we first think of interference, we think of constructive and destructive interference about the classical wave, classical two-dimensional wave, usually, whereas you can also think of it as like a springboard mechanism. You can think of a classical one-dimensional wave, and it would usually be vertical, a spring on a spring. And that here, the mathematics of interference are introduced about the strengths varying, the oscillation varying, the phase varying. Mathematically, we have to find the sum R of two waves. R equals A1 cosine of omega t plus theta 1 plus A2 cosine of omega t plus theta 2. How do we do it? Well, they go on. It is really very easy. And we presume that we already know how to do it. Well, all right. Okay, Feynman. He at least he says, it's like, hey, as long as you're going to be riding your horse up over that cliff there, just don't look down. And then he introduces a rule or a formula about cosine, that cosine A plus cosine B equals 2 cosine of 1/2 A plus B quantity plus, or times rather, cosine of 1/2 A minus B quantity. This half angle formula, or I forget what it's called. But if we know that, then we can immediately write R. We can transform this system of equations and change our formula for the wave in the one in terms of the wave of the other. And we find it with a new oscillatory wave with a new phase and a new amplitude and da-da-da-da-da. And so that's an example of an application of the model to the model to the model. And it's something to follow up in some later date. All right then. Well, good afternoon. I hope there's all to hope for and nothing not to hope for, or what to hope not for. That these notions of what's the obvious and the necessitated and the clear and the what's needed and then what tends. We talked about tends today, and the tendencies and propensities of things. Then we talked about the impasse and the crevasse. That the impasse is a block and an impediment. Reason why we cannot make a cognitive leap otherwise, and that sometimes that's it just means that that's the rule, and so we don't call that an impasse, because the impasse means is that there really is a course to follow there between the infinity of the numbers and the unity of an infinitesimal, or the constancy of an infinitesimal and the infinite divisibility of the numbers is basically the inductive impasse. That is really, in terms of Zeno's paradoxes and how it's arrived at in Aristotle's continuum, that is probably the number one thing to get figured out how to frame infinity in the mind. That it's not necessarily tractable by only inductive inference, that it's necessary to have deductive inference to establish how and why it is so, and fill in that picture. So these are the sorts of things. Then we got talking about matters of style, and Swanson gently and kindly introduced for us a lot of the different things that go into what's going on with d tau and dt and Wick rotation and transformations of coordinates and these kinds of things that had to do, because we're already built way up upon a framework according to what's offered by continuation of the analytic or analytic continuation from the Gaussian results and what's up after the quadrature and what's going on there. That the Wick rotations are because we kind of have some implicit Gauss rotations down there, and so adding up back and forth and together, it allows them to kind of squelch out or squelch is a term from radio that according to the noise on a given channel, you dial down the squelch until the noise is essentially reduced, and you figure anything that comes through and punches through with gain will actually be some signal. So that this noise floor, as it were, is really the same kind of concept that's going on in these terms of these non-measurable paths, and figuring out how to add up really just a discrete finite number of finite things to arrive at a finite thing, when really it's as that's of the root mean square or of a continuous quantity. And then that also gets into some of these definitions of how and why we arrive at these things, like, well, we measure this power in root mean square because that way we can treat it in usual arithmetic formulas in elementary equations, because it's simply empirically so that is tractable by anybody. And so these are the things that go into the reasons why these higher level and lower level readings of things for the dealings of things arrive at that. Now we have a pretty high level science and a theory of science with a theory of probabilistic inference, and after this both inductive and deductive analytical inference, so that then we can have a the physics and a the mathematics of the logic for a clock hypothesis and such things as a hologram of why there's a mathematical universe hypothesis, God willing, as I said. So again, have a great day. It's about the same, just an hour later. So long.